Hey guys, hope everybody's doing all right, and hope the homework's going okay. I've had a couple questions, but um, should be pretty straightforward. But if you have any questions or concerns or anything, as always, just let me know. Okay. Okay. So what I want to do today is talk about uh, talk about degenerate perturbation theory. So far, we've always considered cases where there weren't any degeneracies in the um, energy eigenvalues. And today I'm going to show you what happens if there is, and it's not good. Um, but we'll work through how to kind of work around these situations where you do have degeneracies. Okay, and we're still in the time independent um, realm, so we're not worrying about time. Okay. All right. So what's the problem? Um, so the problem arises because of degeneracies. Um, um, and degeneracies in quantum mechanics arise anytime that there's a symmetry inherent in the system. This is something that you might have seen in the past, either, I don't remember if we discussed it in Quantum 1 or maybe in your undergrad quantum. But anytime the Hamiltonian has some symmetry, there's going to be degeneracies, right? However, if you take the Hamiltonian that has this symmetry and you distort it somehow, you distort the symmetry, this tends to remove the degeneracy or degeneracies if there's more than one. And the way we're going to do that is we're going to distort or change the Hamiltonian by adding on to it a small perturbation. Okay, so we're still going to have our Hamiltonian, which we're going to write in terms of a simple piece. So this would be the piece that we know the solutions for. It has some symmetry, and so there's going to be degenerate states. However, we're going to introduce this new perturbation piece, and this piece, by assumption, is not going to uh, respect that symmetry, and so what's going to happen is that this thing is going to uh, somehow distort the symmetry. Okay, and so we're going to consider a case. Let's consider just for an example. Um, let's say the ground state has Q, where Q is just some number, different states that have the same energy. So the ground state energy is actually Q distinct states. Okay. In this case, we would say that the ground state is what we call Q-fold degenerate. Okay. But now let's suppose that we add on that perturbation Hamiltonian, and that perturbation Hamiltonian doesn't respect the symmetry that's inherent in our simple Hamiltonian piece. And like I said, in general, this perturbation is going to distort, or it's going to lift it should say lift the degeneracy. It's going to distort the symmetry, but lift the degeneracy. And it might partially do it, or it might fully do it. Okay, so if you start with Q distinct states that all have the same energy, depending on the perturbation that you add, it could split it into Q separate states. And that's the case. That's what I have depicted here. So this is the left-hand side here is the initial case. Okay, so you have a ground state, you have some excited state, and so on and so forth, right? But before we turn on that perturbation, there's actually Q different states that live in this, that have the same energy eigenvalue. But then say we flip the switch and we turn on our perturbation, and what happens is that perturbation deforms the symmetry that the Hamiltonian has in it, and that deformation causes this Q-fold degeneracy to split into Q different states, and they all have different energies. Okay, so that's a case where you would have the symmetry fully lifted. In some cases, like we'll see, when you turn on the perturbation, it might only partially lift the state. It might split three states into two states. So still be two states that have that are degenerate. Okay, and so our goal in degenerate perturbation theory is to compute the values of these new non-degenerate energies, okay, and their eigenstates, okay. So the first thing you might ask is, well, why can't we just keep doing what we were doing? We've spent a week or so learning perturbation theory. What's wrong with the perturbation theory? We've learned about why can't we use it? Well, the problem arises, and I think I might have alluded to this earlier, that if you follow this procedure, so let's take for instance the first order correction to the eigenstate, to some eigenstate, right? So we found that the first order correction is some linear combination of the unperturbed states, right? So these the linear combination and these coefficients C and M, and these coefficients are the off-diagonal matrix elements of the perturbation Hamiltonian divided by the difference in the energy of these two states that you're taking the matrix element with respect to, right? Now, you can already see that, in the degenerate case where, say, N and M are sitting at the same energy, right? So they're distinct states. N and M are distinct states, but maybe they're degenerate. And what happens if they're degenerate? Well, the denominator goes to zero, and this whole thing is going to blow up, right? And so our perturbation theory approach is failing miserably. It's failing worst possible way. We always want these coefficients to be small, and here we're seeing that they're blowing up, right? Okay, so the only way out of this bad situation, so we don't want to have to go back to square one, right? It'd be nice if we could just kind of tweak our approach a little bit, right? And one way out of this would be to go back and look at these coefficients, okay? So in the denominator, for the degenerate case, we have the denominator going to zero. What happens if we have the numerator go to zero as well? That would be, that would solve our problem, right? In other words, these matrix elements that are in the numerator, they're off diagonal. Remember, we pointed this out last week. So if we were to somehow be able to diagonalize this perturbation Hamiltonian, then these off diagonal elements would go to zero, and our coefficients would be well behaved, okay? So that's exactly what we're going to try to do in our degenerate perturbation theory, is to try to come up with a way so that these off-diagonal elements vanish, okay? And the way we do this is by constructing a new set of basis functions that are going to be linear combinations of the unperturbed basis functions, okay? But these new functions are going to diagonalize the degenerate perturbation matrix, or at least the sub matrix of it. Okay, so remember, let me go back to this picture. This might help. Okay, so here we have the Hamiltonian matrix, the full matrix that we would build would have all these different eigenstates in them, right? And some of them might be degenerate, and some of them, like say maybe this one, is not degenerate, right? So if an energy eigenstate is not degenerate, then we can apply the non-degenerate perturbation theory that we've been learning about, right? It's only this part that we would have to, do something new to, right? So that's why I call it the submatrix, right? Because it's only a small part of the Hamiltonian matrix that you might have to, do the stuff that we're talking about, okay? So you'll hear me call it submatrix. Sometimes I'll talk about the subspace, but it all means the same thing. It just means we only have to mess with the part of the Hamiltonian matrix that's degenerate, right? And so once we do this, once the off-diagonal elements vanish, and we'll do it by construction, we're free to apply the perturbation theory we've been learning about, okay? All right, so let's talk about diagonalizing the submatrix. Okay, so the primary goal, as I said, of degenerate perturbation theory is to diagonalize these, the submatrix of the perturbative Hamiltonian. right? And the diagonal elements, the eigenvalue, so the diagonal elements, once we diagonalize this, which are nothing but the eigenvalues, that they come out of this process, they're going to be the ones that are responsible. They're going to be the values that are responsible, in a sense, of separating the Q energies. Okay, so if I go back and look at my picture again, right? So we have this degenerate case, we diagonalize it, right? And somehow there's energy shifts here, right? From this original ground state. Well, the difference between the original ground state and, these different levels are going to be the Q eigenvalues, right? So we would have some Q1 eigenvalue that we would add, and it would give us this state, which is a little higher. Or we might have the Q1 state, which is negative, and it'll lower the state. Okay, so the Q eigenvalues are the ones that are get added to the unperturbed energy to give us this spectrum. Okay. Right. Okay. All right. So if we have a Q-dimensional, or if we have a Q-fold degeneracy, then the degenerate submatrix of our full Hamiltonian matrix is going to be Q by Q dimensional. Okay, and so if you have a Q by Q dimensional matrix and you want to diagonalize it, that tells you that you're going to, in general, have Q eigenfunctions and Q eigenvalues, right? So what we're going to do is we're going to define these degenerate states as a linear combination. So there's Q of them, right? These are the, right, okay. So these are the states that we're computing the matrix element with respect to, right? But we're defining these new states, these degenerate states, as being made up of Q, a linear combination of Q, I don't want to say it, linear combination that have Q different terms, okay? I think that makes sense. All right. So by definition, these linear combinations are going to diagonalize H1. So we're just saying, by definition, we're defining these states, and these states, even though we haven't specified exactly what they are, we know that by definition they're going to be the ones that diagonalize the degenerate submatrix, right? So in other words, if I take the matrix element of our perturbation Hamiltonian with respect to these states, it should be diagonal. Okay, so I should get a delta Kronecker delta function. All right, so this is just telling me that I'm in that subspace. So N and P have to be less than or equal to Q, the number of degenerate states. Okay, and so what happens is these new states, like I was saying, once we find what these new states are and the new diagonal elements, we can put it all back together to form the basis for this case, right? So now we would have the piece of the Hamiltonian matrix that's made up of these Q values, and then we would have some pieces that are non-degenerate, and so on and so forth. So that's what this is showing here. So you can see that these states here are degenerate, right? And these states are non-degenerate. Okay, so it's just showing that the full Hamiltonian in general doesn't have to be all degenerate or all non-degenerate. It can be a mix of both. Okay, so this would be kind of the set of eigenkets. Okay, in a picture, the perturbation matrix would look something like this. Okay, so we would have out here, outside of this little dotted square, if you can see that, would be the, let's see, that would be the non-degenerate terms, right? It's the Q plus 1 term and higher. Whereas here, this is the degenerate space after we've diagonalized it. Okay, so you can see what's happening here is that you just work with this submatrix of the full Hamiltonian matrix. All right, so as always, right now we're just talking about the formalism. We'll work through plenty of, a few examples so you can get a feel for this. And there'll be plenty of homework problems on it too, so don't worry. All right, so now what we would like to show is that the diagonal elements of the submatrix are those first order energy corrections. In other words, they're the terms that you add on to the unperturbed energy eigenvalue to get that full spectrum. Okay, so let's try to show that. All right, so what we want to show is that these first order energy shifts are indeed these diagonal matrix elements of this diagonal submatrix. In other words, these guys right here. Okay. And if we find that, these diagonal elements are all mutually distinct, in other words, there's Q different, there's Q of them and they're all different, then we would say that the Q-fold degeneracy is completely removed or lifted by this perturbation Hamiltonian. Okay, so let's try to establish this. And to do that, we're going to first write down the Schrodinger equation or the eigenvalue equation for the total Hamiltonian. Okay, so I have the Hamiltonian hitting our original states. The original Hamiltonian is made up of the simple plus the small piece. And on the right-hand side, we've got the energy eigenvalue multiplying the same state n. Okay, so next what we want to do is we want to assume that the unperturbed state is Q-fold degenerate. All right, so in other words, we have Q degenerate states, and for n less than or equal to Q, we're going to make some substitutions, right? So in other words, we're going to substitute instead of this state, we're going to plug in our degenerate states, right? And the energy is going to be made up of the unperturbed plus the first order piece. Okay, and we're going to plug these into this equation here, right? And so when I do that, the left-hand side, which is this, is going to become, so the only thing that's really going to change is this n hat value, right? But now when H naught hits this guy, it's going to give me the 0th order energy. So this is the unperturbed degenerate energy, right? And then I have my perturbation Hamiltonian still hitting this n hat state, okay? And the way we got this energy eigenvalue is because we know that this state is degenerate, but remember it's made up of it's a linear combination of all the Q degenerate states, right? But all these states have the same energy. So when the Hamiltonian hits this guy, it's going to have the same energy as if it hit just one of these guys. Okay. All right. So that's how we got that term there. Okay. And so that's the left-hand side. The right-hand side of this equation, right? We just have to plug in this guy for E, and then make the change in the eigenkets. And so what I end up with is something that looks like this, right? And when I equate these two sides now, I can see that the 0th order part is going to cancel out, okay? And so when the 0th order part cancels out, it's a mouthful, you find that you get an eigenvalue equation that looks like this. So this is the first order, so this is the perturbative Hamiltonian, and we get a first order energy correction, okay? So remember, it's important to remember, because this is a point that a lot of people get confused on. These new states that we're defining with the hat, they are not perturbed states. Remember, they're linear combinations of the unperturbed states, and their coefficients are just normal, normal type of coefficients. They're not like coefficients like what we had when we were doing perturbation theory. Okay. So if we just count it up, right, well, I'll just leave it at that. Okay. So let's assume that we've constructed these states correctly, and they form an orthonormal set, right? So these are, remember, these are eigen cats that diagonalize the submatrix, so they should be orthonormal or orthogonal at least. So now let's take this guy and multiply it from the left by an eigenbra. Right, so this eigenbra I'm going to call p hat. Right, so when p hat hits over here on the right hand side, p hat on n hat, they're orthonormal, so it's going to give me this delta function, right? And then I have p hat and n hat sandwiching my perturbation Hamiltonian, right? Right. And so what we can do is this delta function is telling me that it's going to be 0 unless n and p are the same, right? So what we have really is the first order energy shift is the diagonal elements of this perturbation Hamiltonian, right? And that's exactly what we set out to show, that the diagonal elements of this degenerate submatrix are the first order energy corrections to the unperturbed states, right? And you see that it takes the form, the same basic form that we found in unperturbed or and non-degenerate perturbation theory. In other words, that the first order energy shifts are the diagonal matrix elements. Okay, here we just had to go through the extra step of actually diagonalizing the Hamiltonian. Okay, so now what we can do is we can construct these new basis functions, right, which diagonalize the degenerate space. Okay. All right. So as we've already seen, we can write these guys in terms of expansion coefficients, and we'll call those AMN. Right. So remember, this guy is just a linear combination of these guys, so it's still zeroth order. Okay. And I can substitute now this into our eigenvalue equation. So I can go back to my eigenvalue equation here, right, and substitute in this expansion. Okay, so that's all I've done here. All right, and now let me multiply this from the left by, again, our eigenbra. Okay, so these are the unperturbed eigen. This would be an unperturbed eigenbra. Okay, and so when I do that, I get this off diagonal matrix element times this coefficient being summed over, and over here I get a delta function in P and M, right, and then my energy that I can pull out in front, right? Or I can pull everything over to the right hand side, right? And if I do that, then I can pull out that coefficient, and I get something that looks somewhat familiar. I get a Hamiltonian minus eigenvalues being multiplied by an identity matrix. Okay. Oops. Right. This is all within the degenerate subspace. And so what this is basically is because we're summing over M from 1 to Q, right? And we can look at this. We know these are matrix elements, and these together are matrix elements, right? And we're multiplying this thing and summing over one of its indices. So this is nothing but a matrix being multiplied onto a column vector. Okay, we've seen this several times, right? And for each value of n and p, right? So n and p are open indices. So for each value of n and p, it gives us one equation for E sub n and the q components of these column vectors. Right, and there's q. You can convince yourself there's q such equations corresponding to the q values of p. There's a lot of letters involved in this, but it should make sense. Okay, just know that we're in this subspace, so p and n are constrained to be less than or equal to q. All right, so for the ground state, so let's say for n equals 1, you can write down these equations, right, in a matrix form, right? So in matrix form, it would look something like this, right? So you see all my Hamiltonian matrix elements, and then here I have I'm subtracting off the piece coming from E multiplying the identity matrix, right? And we can get, for any value of n, say we went to n equals 2, we get the same thing. We just have to change all, these indices from 1 to 2. And actually, we could just do this all the way up to q. Okay, so we would get these matrix equations for each value of n. Let's see. Right. Okay, so what we're looking for is solutions to this matrix equation, right? And if you're trying to solve this matrix equation, hopefully this looks familiar, because it looks a lot like I can't think of what it's called now. When you're diagonalizing the matrix. I know you guys are probably yelling it to me right now, but I can't think of it. Anyways, it's I almost had it. I was right on the tip of my tongue. Okay, but anyway, so the way we find a non-trivial solution is by taking this thing and taking the determinant of it. Okay, and in this situation where we're solving this type of these degenerate subspaces, it's known as the secular equation, characteristic equation. Okay, so it's when you're solving for eigenvalues, normally it's called the characteristic equation, but in this case, we call it the secular equation. Don't ask me why, but that's just how we'll refer to it from here on. Okay. So the Q roots of these equations are going to be the eigenvalues of the unperturbed Hamiltonian, or the perturbed Hamiltonian, right? So that's what we're doing. So we're diagonalizing this, and it's going to give us Q different values, Q roots, Q eigenvalues, right? And those are going to be the guys that we add on to the unperturbed energy to give us the new spectrum. Okay. And then we'll be able to take those eigenvalues, plug them back into the eigenvalue equation, and then construct the new states, right? The new eigenstates. And these eigenstates are going to be, or we can always write them as linear combinations of the original or the degenerate states. All right, so I would go back here and plug in, and I would solve for these new eigenstates, and they're going to be linear combinations of the states that we started with, which were degenerate. And just to stress again that these states that we construct, they're not perturbed states. So they're not like the first order states that we constructed when we did non-degenerate perturbation theory. They're what we call the new zeroth order states. Okay. Most of the time we won't be concerned with computing corrections to these eigenstates. So we're, sticking to just these new zeroth order states is enough. Okay. And that's it. It's that easy. I'm just kidding. We'll see plenty of examples, okay, of how to do this, and it'll become clear. But I wanted to go through the formalism so we can, we'll have that in place. And next time, what we'll do is we'll start to look at some examples. And I think we'll start like with three-dimensional square well, right? An infinite square well. Okay, and that system has non-degenerate states and some degenerate states. In fact, it has a lot of degenerate states. But I'll show you how we can put all this to work. Okay, so just to summarize, this is the kind of general algorithm. All right, so if you're given a state or given a problem, the first thing you want to do is identify the degenerate unperturbed cats. Right. So you would write down, your Hamiltonian, maybe in a matrix form, and you'll identify the states that are degenerate, and then you'll want to construct that submatrix, that perturbation matrix, right? And then from there, it's just pretty much turning the crank, right? You want to diagonalize that perturbation matrix by solving the secular equation, which is much like the characteristic equation. And then we'll identify the roots of this equation as the first order energy shifts. Okay, that we've seen a couple of times now. Okay. And then finally, we'll feed those back in to this matrix equation and solve for the new eigenkets. And these new base kits are going to be the ones that diagonalize our perturbation matrix and are the correct or the new zeroth order kets. Okay. And that's how we get around the problem of the denominators blowing up whenever we have degeneracies. Okay. All right. So that'll do it for today. And I'll see you Friday. And I don't remember when the homework's due, so that's to your advantage. But just get it to me soon. If you have problems with it, let me know. But just get it to me as soon as possible and in LaTeX form, preferably. But all right, I'll see you next time. Take care and have fun doing quantum mechanics. Bye.